All right. What I want to do next is I want to show you how to find the Laplace transform of f prime of t. Clearly, derivatives are going to be useful here if we're going to use these to solve differential equations. And this is going to turn out to be some calculation that we're going to use integration by parts with. What we're going to do is just do the calculations, not paying attention to any of the details. And then if necessary, we'll go back and we'll think about what are the different assumptions that we needed on our function f or f prime, or what did we really need to make this argument work. So all we're going to do for now is just plug everything in according to the definition. So this will be e to the negative st, f prime of t dt. And we're going to do integration by parts. Clearly the function that we're going to want to integrate will be f prime. And that means that we're going to want to differentiate the other function. And so this is going to be f of t, e to the negative st. And that's going to be evaluated from t equals 0 to infinity. And what we're going to do then is subtract the integral. Let's see. We've integrated f prime, so that means that we have f. And then we differentiate e to the negative st with respect to t. So that's going to be minus s e to the negative st times f of t dt from 0 to infinity. And this first function, f of t e to the negative st, what we're going to do is we're going to assume that as t goes to infinity, this is going to be 0. So we're going to assume that f is exponentially bounded, but we need f to be exponentially bounded anyways in order for this last part to make sense. So this is going to be, actually before we get to the last part, there's one other thing here. So this is when t goes to infinity. We're going to subtract what we get when t is 0. So we're going to have f of 0 e to the negative 0, e to the negative s times 0, plus s times, this is a Laplace transform of little f, so I'll call that capital F of s. And let's see, then we're done. This is going to be s, capital F, minus little f of 0, and that's the Laplace transform of f prime of t. And so we needed, all we really needed here, all that we needed was the assumption that f is exponentially bounded, right? That f of t in absolute value is less than c e to the minus mt for all t, right? Okay, in other words, the only assumption is that there exists constants c and m that make this hold true, right? F is exponentially bounded. Exponentially bounded functions are going to be functions that we're going to work with anyways. So it's not really a big assumption on our part, but that's what we need to make this argument work. So this is worth just filing away. By the way, I'm going to add, I have a list of all the transforms that we're going to use over the course of this chapter, and I'm going to add that to the modules link on Canvas. Okay, so I will add that. All right. So now what we can do is we can solve differential equations, and maybe let's solve, I just want to make this an easy one just for starters. So let's solve x prime of t plus 4 x of t is equal to 0. Subject to the condition that x of 0 is 1. I'm just making this up as we go. And what we're going to do, and what we're going to start with, using this Laplace transform method, is we're going to take the transform of both sides. So the Laplace transform of x prime of t plus 4x of t is going to be equal to the Laplace transform of 0. Okay, the Laplace transform of 0 is just 0, by the way, because it's 0 times 1 over s, but it's 0. And by what we know about the Laplace transform, this is going to be the Laplace transform of x prime plus 4 times the Laplace transform of little x. Okay, and so that's going to be equal to 0. So let's move that 0 over. And what we can do now is use what we know. We know that the Laplace transform of a derivative, so now I'm just going to use this formula that we just developed here. But the Laplace transform of x prime is going to be s times capital X of s. Remember that if little f is the input, capital X is the output, minus little x of 0 plus 4 times capital X of s equals 0. And so what this is going to be is, let's see, we're going to get s times capital X of s minus 1 plus 4 times capital X. And now our job is to solve for capital X. So I'm going to get the 1 on the other side and factor out the capital X on the left. So we have capital X of s times the quantity s plus 4. That's equal to 1. And that means that capital X is equal to 1 over s plus 4. And so our final step is to take the inverse Laplace transform of both sides. And if we take the inverse Laplace transform of both sides, we're going to end up with, let's see, so the inverse Laplace transform of the Laplace transform capital X is little x. And the inverse Laplace transform of 1 over s plus 4, the inverse Laplace transform is going to be e to the minus 4t. And so this is our solution to the differential equation. X of t is e to the negative 4t. Okay, that's our solution there. And again, that's the one and only one function that has both of these properties. So where x prime plus 4x is 0, so that makes good sense because x prime is negative 4 times x. So when you add that to 4x, you get 0. And when t is 0, x is 1. And that makes sense as well, right? X of 0 is 1. So this is the one and only one function with these properties. While that's a simple example to absorb, the idea is going to be the same throughout the whole chapter. The whole idea is you start with the differential equation, you take the transform, you use everything that you know about transforms until you get to a point where you can take the inverse transform. And somehow taking the transform and then later taking the inverse transform, based on everything that we know about the transform and all its properties, somehow reduces this and solves our differential equation. Okay, it's very nice. It's a very nice method that we can use to solve differential equations in general. Okay, so we'll work on solving more and more sophisticated differential equations as we go on. Of course, I feel compelled just to point out, if I ask you this question on an exam, solve this differential equation given this initial condition, it's perfectly reasonable to use the Laplace transform. It's totally fine. I shouldn't say it's reasonable. It's not reasonable. But it's totally legal. It's one way that you could solve this problem. And in fact, this way is actually how many of the computer algebra systems solve. This is how many computer algebra systems solve differential equations, is with this transform method. And you can tell by the way that, say, Wolfram Alpha, the way that it spits out the answer, you can tell it's clearly doing a Laplace transform. Anyways, but if this question was on an exam, this is a terrible way to do the problem, right? Because really all we're trying to do is we're trying to figure out what's the function x where x prime, so what's the function where x prime plus 4x is 0. This is a separable differential equation. This means that if I were to move negative 4x over, right, dx dt would be negative 4x. That means that 1 over x dx is negative 4 dt. Integrate both sides. Natural log of x is negative 4t plus c, which means that x is c e to the negative 4t, and then you can get c equals 1 by using the fact that x of 0 is 1. This is a much faster way to solve the problem. But the Laplace transform is really there for a few reasons. There's types of problems that we can solve with it that we can't solve any other way. It's a good introduction to the Fourier transform, which is something super useful. The Fourier transform, I should mention, is not terribly useful for ordinary differential equations. It's useful for partial differential equations, which is kind of a second course follow-up to this one. But the Fourier transform is super useful for figuring out solutions there. Kind of doing a similar thing that we're doing here, but there's a little bit more to it with the Fourier transform. So if this is given on an exam, the Laplace transform method works, but it's certainly not the best way. Despite that, we're going to see its utility as we go along.